Hello and welcome to the show. My name's Relevant. This is Do All the Things. If you've been following the comedy, on previous episodes I've built numerous effects pedals, and some of them with the most simple circuits. They don't play well with AC adapters, they have to run off batteries. And when you're building these circuits yourself, you can fine-tune, calibrate them to slightly different voltages. And because I don't want to be the kind of person who blows through disposable batteries, I invested in rechargeable batteries, which I, of course, could calibrate my pedal to run off just the slightly lower voltage, and they've worked wonderful. Now the thing is, I don't actually have a 9-volt battery charger. Lucky for me, new nickel metal hydride packs with low self-discharge come pre-charged, so I could start using them right away, but I'm gonna have to charge them eventually. I went looking for various chargers, and you can get like really cheap ones that you don't want to trust off Amazon and eBay, and then you can go to the hardware store and buy an expensive one that does all of the batteries. I just want to charge 9 volts. So I decided, well, I'm just gonna build one. We live in a day and age where battery chargers are extremely common, and jelly bean parts to build them can be had. Just a quick search through Mouser or DigitKey. If you look in the power management IC sections, you can find battery charger chips, battery charge controllers. Some of them are stupid simple, and some of them not so much. Either way, if you do find one, chances are it's going to be a little SMD type component, which can be intimidating for some. One of the simpler circuits I was looking at was a 10DFN package, and I'm like, I don't know if I can solder something that small. Turns out I can, I since have. But at the time, I decided to choose something more standard in an SOIC 16 package. And in fact, it's not the simplest one. This is what I settled on. It is a Maxim DS2715, specifically a charge controller. And this guy's interesting in how it works and what you can do with it. It says to support up to 10 NiMH cells and a 2C charge rate. I wonder how they come up with that number, because the way this thing works, I see like a whole lot of potential for it. However, it does have limitations, and I'm gonna go over that here. In the data sheet, they were nice enough to give you a rough schematic on how to use this thing, and there's two versions. There's the linear application, where they use a Mosfet as basically it regulates via an adjustable resistor, if you will, a linear regulator, just letting a certain amount of juice through and bleeding off the rest. But there is a more efficient version that has an actual switch mode controller on it, where you have to add kind of a bootstrap MOSFET driver for the fat switching and the Schottky diodes and the L1 or inductor. I did test that circuit. It does work. A little bit more finicky to dial in, but it's because the switch mode is more designed for a higher current application. For a current application as low as we're going, I'm going with their linear circuit because it's simple and it works well. Now, a rechargeable nickel metal hydride 9 volt, they have a rating of something like 175 milliamp hour. In practice, you might get about 150. And then that begs to question C rates. C rates is one of the first things you have to think about when you're designing a charger, because batteries have a maximum current you can charge them at. A nickel metal hydride battery, typically there's not much of a problem doing it at about a 0.5 C rate. So what that means is if you take the capacity 175 milliamps and multiply that by 0.5, which roughly computes to 50%, that means we can charge it up to 87 milliamps, especially if we have an intelligent charger that knows how to cut it off. You don't want to do that the way some trickle chargers work, and trickle chargers are annoying. Let's not go there. Now, the design I came up with is ultimately going with a 0.4 C rate. I'm targeting 70 milliamps. So then, how do we take this and make it work for us? I gotta sneeze. Now, this particular schematic looks complicated at first, but the more you look at it, the simpler it gets. And also, this schematic, I think they drew it up to show you the potential of what this thing can do or what they intend it to do. For instance, you see this thing up here that says load. Well, what the frick is that? It's literally whatever the device you plan on powering off of the battery. This particular schematic is based on the idea that this charge controller is going to be installed in a fixed device, like say I don't know, a friggin' old laptop that had nickel metal hydride batteries, this might be the charge controller that would be inside there. So the load would always be hooked up to an internal battery pack. The charge controller would live inside the device with the battery pack, and then when you plug in power, it would kick on the charge while simultaneously powering the load. When no power is applied, the batteries can backflow through the MOSFET here, because you see the MOSFET, they have these little diodes in them, and a P-channel MOSFET, which is what is spec'd out here, it can allow power to backflow through. And in some cases, depending on the rating of said MOSFET, it can handle a fair amount of current. So it just works. Now this is not applicable to the way we're going to be using it. So I have to change this up a bit. So over here we see the battery pack. And then just to get the simple out of the way, that's an NTC thermistor 10K. There's something to balance it. I do believe if we delve deeper into this data sheet, we'll find that we could probably use this value to recalibrate other value of NTCs, but 10K is common, so we just use that. We have this voltage divider across the battery pack going to something called VBAT. That is what allows the charge controller to detect that there are batteries installed and what voltage they are. And you basically set this voltage divider so that VBAT sees the voltage of an individual cell. So there's some math to compute this. Over here is the MOSFET. VCH controls that MOSFET. This is what dictates how much current, how much voltage is going to flow through, and this is how the controller controls the charge rate. Now VCH is what's called an open collector to ground, which means all it does is it lets a negative pass through, and if you know a P-channel MOSFET, negativity turns it on, positivity turns it off. But it's only open collector. It doesn't put any positive signal, which is what this guy right here is about, this R3 and capacitor combination. That's basically a pull-up resistor. So when VCH is doing nothing, this allows positive to pass and turn off the MOSFET. And then VCH kicks on to turn it on. D2 and R2 is apparently a trickle charge circuit. So when it's not charging at all, this would let a little bit of juice pass through just to keep the batteries topped off. And you know, based on 6 volts and based on our battery pack, we would set the value of R2 to allow the C rate we want. I think this is roughly 1/10 of a C rate they got set up here. I can't remember. Why? Because I don't care about that. We're not interested in a trickle charge. When this thing's done, we remove the battery. So we're just going to be omitting that. Of course, right here we have an LED output, the resistor to bias the LED, and then the LED itself, and it blinks when it's charging. When it's done, it goes dark. We have the power input for the chip itself through this 150. We have an RC network here of a 0.1U standard in all ICs to filter its just power right in on its power pin. That R50 allows just the slightest hint of voltage drop so that that capacitor could filter better. And then of course right here we have a 47U. That's our main reservoir capacitor to keep the power fueled to the circuit. I do not understand why they have a 47 and a 1U next to each other. That seems strange to me. Why not just have a 48U? Because they don't have 48Us? Was 47 not quite enough? I don't have an answer to that question. Here we have a Schottky diode which stops power coming off the batteries, backflowing the MOSFET, going to the load from backfeeding to the output. And this is important because of this pupper right here, the 2N7002. This is part of the timing circuit. To charge a nickel metal hydride battery, there's 2 ways that you terminate it: heat and time. Believe it or not, a lot of nickel metal hydride chargers, they know the battery is charged when it starts overheating. They detect a temperature rise. In the case of this guy, if the temperature of the battery goes up more than 0.5 degree a minute, it knows it's at capacity. They will charge cool until they get full. They'll start to warm up. Other than that, you have to use time, which means you have to know the capacity of the battery and you set a timer on the chip. The unfortunate thing about nickel metal hydride batteries that makes them a pain in the arse to work with, unlike say a lead acid or a lithium ion, is you can't constant voltage charge them. You might have a battery like this, rated for 8.4 volts. But as soon as you put charge voltage to its pin, it skyrockets. It's instantly going to hit 9 something. While it's being charged, it will go upwards of 10 volts for the pack. And then you notice it might sit at 10.5 around the end of the charge, but as soon as you pull it off, it kind of dips down to 9.9. Then you let it sit and settle for a while and you measure it, it's 9.7, 9.5. What I'm getting at here is you cannot judge the charge state of these nickel metal hydride batteries by the voltage of them while they're being charged. So That's why the chargers have to do this. They have to use trickery, like time and temperature. They call it DT, something to that, except they use capitals and lowercase to blah, blah, blah. Which brings us to the timing circuit. RT is the resistor timer, and it's basically this resistor right here of 86K sets how long the charge is going to last for. You change the value of this based on how long you want it to charge. And that's where this 2N7000 comes in. Because you can see, they put the Schottky diode before the power input for the circuit. So in theory, as long as batteries are connected, this charge controller is powered. And this charge controller has some form of battery management on it where it just kind of monitors the cells in some way and recognizes that it's in discharge mode, that the load is pulling. I don't know what it does about it. That wasn't exactly clear, other than it makes sure that this MOSFET is fully shut off. But that means that if power is connected to this, that timer will keep running, and that's where the MOSFET comes in. That's an N-channel MOSFET, which is turned on by positivity, off by negativity. We got a pull down resistor here to ground that's going to keep it turned off until you plug in power here. Then positive is going to hit that thing, kick it on, pull that resistor to ground, which is going to start the timer. So there's one last aspect of this circuit left, and that's this pupper right here, R7, a very important component. You see, we have ground coming in, and then we have our negative for these capacitors up here, and then we have sense plus. Then it goes through this resistor, a line goes directly to sense negative, and pretty much all the rest of the ground connections are connected after this. That's a current sense resistor, and this is how the charge controller knows how much current is being drawn so it can set the amount of current via the MOSFET. Now, this resistor is also how we program our charge current. In linear mode, it's different in switch mode, but in linear mode, this charge controller sets the current by setting the voltage drop across this resistor to 0.121 millivolts, which means it will adjust this MOSFET to keep the drop across this resistor at that set voltage. So we basically change the value of this resistor to set our current. So once we got this all figured out, it's actually pretty simple, except for all the frickin' math, bud. Now, seen here is my version of the schematic reflecting my application, because the datasheet tells us how they have it set up, but our application might be different. So you gotta kind of be able to read between the lines. So here we have our 9-volt NiMH pack, and then the values that don't change, I have left there. We have a 10K. There's this C bias pin that I'm not exactly sure what it is, but you need a capacitor to ground. Mode sets the mode. You would attach it to C bias if you wanted switching. There's actually 2 connect to ground pins and 2 VSS pins that all have to be hooked up. There's our MOSFET. We're moving the Schottky diode here so that when the charge is finished and the power is unplugged from the box, if the battery happens to be on it, it doesn't backflow and fire up the circuit. We don't need this circuit to run when there's no power applied. That's going to prevent confusion in the timing circuit. And of course, the positive connections are before there. Most of it is the same, except I've changed up the timing circuit with this pupper right here. That is a 74HC1G14. It is but a single solitary Schmitt inverter. Schmitt inverter, one of my favorite components. So basically what happens here is we have an arbitrary 10K resistor with a 5.1 volt Zener diode to set the power supply for this pupper so it can work. These guys, the logic, it's 5 volts, 6 volts max. We can't run it off the 12 volts it's gonna run. So that's just a very basic power supply. I should probably have a capacitor there, but I don't. The output is going to be on the timing resistor. Now, if you know how output logic works, the output pin is either going to be high or low. It's either going to be tied directly to positive or directly to negative. There's going to be no intermediate Z state. So what happens is when this guy switches on, it's going to pull that resistor right through directly to ground. And how do we turn it on? We have this 1 meg resistor connected to the battery side. So as soon as a battery is inserted and it detects a little bit of voltage, that positive voltage is going to cause the inverter to swing low on the output and connect that resistor to ground. And then our timing is going to kick in. So we can power it up. In some of my testing on this circuit, as soon as you power it up, it could start timing, right? And then with a battery uninserted, well, we would have a path through that 1 meg, through our resistor divider network here to ground. It would see low, it would put positive here or high here. High is only going to be the potential of this 10K resistor. The little IC itself needs microamps to actually work and do its job. So putting high to this pin is effectively going to turn off the timer, and with 10K we don't have to worry about too much current hitting it, especially not with the resistor itself. I've omitted the 1U, I'm sticking with just A47. I've tested this, it works, so I haven't felt the need. Some other thing that I've tested is, you notice CTG and VSS are after the current sense resistor. They actually do have to be there. Now, I tested mode, C bias, and the 2 CTG pins before current sense, and it still seemed to work fine, though I could imagine they have the reasons for doing that. The 2 VSS pins absolutely have to be after current sense. When I attached them before current sense, the circuit went all cattywampus and started doing funny things like way too high charge rates and whatnot, which kind of throws a little bit of a monkey wrench. Because here's the thing, that current sense resistor is not only going to be sensing the amount of current that hits the battery, it's going to be sensing the amount of current that the charge controller itself is consuming to run, which, as you're going to see in the math, is about 10 milliamps. So whereas that is nothing if we're building something charging 1 amp, that greatly affects our math when we're dealing with tens of milliamps at charge rates like this guy. Which brings us to the math. So the first thing we have to calculate is this resistor network, and the math is actually really simple according to the data sheet. We basically take the number of cells we have minus 1, so in this case it's 3 cells, minus 1 is 2 cells, then we take the value of this guy and multiply it by 2 cells. And that's how we come up with 200K. Basically, this resistor reflects 1 cell, and this one's going to reflect the remaining cells. So if we have 7 cells, like we do in one of these batteries, and don't quote me on that, because some nickel metal hydrides are going to be different. I had to kind of do some research to figure it out, but I confirm that this guy here, I believe, has 7 cells. That's the design spec. So obviously that math would be basic. 100 here, 600 there. We don't even have to compute. 600 is an oddball value. So if we're going to buy oddball values, and in actuality, I couldn't find a 600K. Instead, I got a 124. Because of an existing project where I built an Interfax HP1, I got some oddball values in stock. One of them's a 750. So I computed for a 750 up here, and I got 125 here. I was able to purchase a 124, close enough. So we're gonna punch those poppers in. That's gonna be a 750, and that's gonna be a 124. If we want to expand on the math just a little bit, the voltage the VBAT pin is looking for is 1.55 volts. Multiply that by 7 cells, you got 10.85, which is good because if you look at 9-volt battery data sheets, that's about their maximum cutoff voltage they want you to go to. And I found because of the load these put on the surface, even if you force them a bit harder, it's not going to exceed that. And if we go 100% divided by 7 cells, we get 14.2857%. And indeed, 10.85 multiplied by 14.285% is 1.5499 blah 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 blah. So you see how that math works out. So if we have a 750 plus a 124, we have 874. To calculate the percentage, it's going to be 124 the bottom divided by 874 the total. Oh, we're at 14.187, or rounded up to 188%. So if we take 10.85 volts now, and we multiply that by the 14.1877, we're gonna see our voltage at VBAT is a little bit lower, but this thing, we're gonna see that that is pretty freaking close. Now, because this thing doesn't use voltage detection for its battery cutoff, that's close enough. According to the data sheet, you need it to be between 1.5 and 1.6 volts for that function to do what it needs to do. So what's next? We got this pupper right here, this value we have to set, that pull-up resistor. So apparently VCH, being an open collector, has a maximum capacity of about 20 milliamps. So we have to set the value of this resistor so that no more than 20 milliamps is gonna flow through here. Target is 10 milliamps. And this is where that parasitic current draw after the current sense resistor is going to be problematic. Now, we're going to be running off a 12 volt supply. The math is real stupid simple. We just use Ohm's law. 12 volts divided by 10 milliamps, or 0.01, is going to give us a value of 1.2K, which I have in stock for some reason. That's kind of great. An LED, well, that has to be able to run off 12 volts too. Now, there's some debate on how to bias an LED, compensating for the voltage drop, but I just quick and dirty use Ohm's law, pretending like the LED doesn't exist. So of course, 12 volts divided by 0.005 milliamps is what we would use for just a basic indicator LED. We get 2400 ohms, 2.4K. Close enough is going to be a 2.2K. Down here, current sense. Now remember, this guy sets current by trying to maintain a voltage drop of 121 millivolts right here. So my choice of 70 milliamps was half circumstantial based on the values of resistors I could get and have to work with. And actually I ordered a variety of low impedance resistors to kind of tune up this circuit. And the one that I chose was close enough. We went with 70 milliamps, but this circuit is going to consume 10 milliamps in and of itself. So we want a total of 80 milliamps. So if we have 121 millivolts, according to their math, which is based on Ohm's law, we divide that by 80 milliamps and we're going to get a value of 1.5 ohms. This math's all explained in there. So if it looks a bit arbitrary the way I'm crunching these numbers, well, RTFD. So this becomes a 1.5 ohm. Z is used as a representation of ohms under circumstances in which we cannot draw the little ohm symbol. Now we just have to figure out the timing. The math for that is also real simple. It's going to be in minutes. So we have a 175 milliamp hour battery and we want to charge it at 70 milliamps. That's going to be 2.5 hours that we need to charge this thing. 2.5 hours multiplied by 60 minutes per hour is a total of 150 minutes. We divide that by 1.5 and we get a 100K resistor. So yes, the result is in K, and 1.5 is an arbitrary number on their end. It has nothing to do with the current sense resistor we're putting in. That wouldn't change to 3 if we were using a 3 ohm resistor. It's always 1.5. That's based on their internal math. So that would be real freaking simple if it wasn't for the fact that this charger has 2 stages. It has a fast charge and then it has a slow top off charge. It does that fast charge, whack at the battery with all the juice, and then at some point it stops either from time or temperature, and then it goes into a slow charge state. The slow charge state will be exactly half of the timer that we set. So if we set a 2.5 hour timer, we're gonna get a 1.25 hour of slow charge. So that would be a total 3 hours and 45 minutes. So that means there's capacity being juiced into this buddy after the fact. And I'm thinking, you know, 100K is good because the data sheet pretty much tells you, go ahead and set that value for the capacity of the battery at fast charge. I guess the slow charge is a bit arbitrary. But what I did is I complicated things. A little bit more. And I also wanted to use up more oddball resistors like the 91Ks that I got for the HP1 build. So let's see what we got here. If we reverse the math, we start off with 91K times 1.5. We get 136 minutes. Divided by 60 is 1.275 hours. Multiply that by a 70 milliohm charge rate, and that's a capacity of 159 milliamps, which is bang on the realistic capacity of this. Now, compensating for slow charge. The slow charge works by setting the voltage drop across the resistor to 33 millivolts. So we go 0.33 divided by 1.5 ohms. We're doing the math backwards here. We get 22 milliamps. And of course, we have to take away 10 milliamps because of losses. We get 12 milliamps. And if we divide our original timing by 2 to get the slow charge rate, we multiply that by 1.1375 hours. And we get 13 milliamps of charge in that last 1 hour. We add that to the 159.25 we get in the main charge, and we're at 172.9 milliamps, which is perfect, because if you think you're getting the advertised capacity of a battery like this, you're probably not. Or, you know, we just put a 100K in there. It's just kind of weird. It's gonna burn for an hour, doing very little. But either way, 91 to 100K is gonna be our value there. Maybe I'll make that socketable. So that's the math and that's the circuit. And to make this work, here is the layout that I've come up with to put out ce petit perf board. Oh. Now let's build on it in the next video, because I'm separating these two videos, because some people like build videos and some people like math videos. And if you watch this, you like the math video, but there's people who probably didn't want to watch this math. So stay tuned for the build if I haven't posted it first. Hey, I did a hand gesture without even thinking there. Finger guns. I'm not a finger gun person. Why is that coming out of this?